Okay, now I just want to point out some common mistakes you need to look out for. These are pretty common when you're breaking logs apart and expanding them. It's pretty common for a student to try to distribute a log across addition or subtraction. But you can't do that. The log base b of x plus y, you can't break that down any further. You can't distribute. That is not equal to the log base b of x plus log base b of y, because by our rules, this part, log base b of x plus log base b of y, is equal to log of x times y. Log base b of x times y, not plus y. So you cannot break apart addition inside the logarithm. In the other direction, a lot of times when people are combining the logs, I see them write too many logarithms. The log base b of x divided by y as inputs is not the same as having log base b of x over log base b of y. When you're combining, and where you see this most often is when you're combining logs by the rules, like if I had log base b of x minus log base b of y, it's a single logarithm where you divide the inputs. That's very different than dividing the outputs out here with logs on each one. Okay? And then this third one, you have to be a little careful when you're doing powers. Usually when you see a power with a logarithm expression, it's meant to be on the input. You're talking about log base b of x to the n inside the logarithm, which by our rules is equal to n times log base b of x. Now, if the power is on the outside of the expression, it's actually very different. Like I would ask you to look at log base 10, the common log of 10 squared with the power inside and outside the log, and see that you actually get different results there. So if you actually mean to square the entire logarithm, you have to do that, or raise to the power of n the entire logarithm, you do that on the outside. So it's an important important distinction between whether or not the power is on the inside or the outside of the log. Okay, and then one last thing in this section, we can now come up with what's called the change of base formula, which is not as useful when you have the super fancy calculators, because the brand new TI-84s can actually, you can evaluate log base 2 of 5 directly with a little template, but a lot of calculators you can't do that, and before, up until a couple of years ago, we couldn't do that on a TI-84 either. But you can turn log base b of something into a natural log or a common log expression with what's called the change of base formula, and here's the proof of that. So suppose you want to actually evaluate log base b of x, where you have numbers, like you want to do log base 2 of 5. Okay? Well, we could call that expression y and then kind of symbolically solve here. So by definition, b to the y equals x. That's what we're trying to do. I'm trying to figure out what power of 2 gives me 5 down here. What power of b gives me x? Well, you could take a log of both sides of any base you want, and what we would do is use natural log or common log. That way we could evaluate this on a calculator. But you can use any base. Do log base a of both sides, and then you can drop the power and then just divide, and you get y as log base a of x divided by log base a of b. So what this is saying, the change of base part, if I want to evaluate log base b of x, I can do log base a of x for any base I want, as long as I divide by log base a of the original base, b. Okay? So I can do this with common log or natural log. If I want to do log base 2 of 5, I can do either the common log or the natural log of 5 divided by the log of the base that I want. Okay? And you can use common log or natural log as long as it was the same log on both sides of the equation, or when you get to the formula, the same log on top and bottom. Okay? So if you want to do on your calculator log base 2 of 5 on any calculator that has logarithms, you could do another log of 5, but that's base 10. You just divide by the log of the base. If you want it to be base 2, divide by that. Okay? And you get the number that 2 to this expression will give me 5. I could use natural log. Now individually, natural log of 5 and log of 5 are very different, but when you do the ratio, it works out to be the same, as long as you divide by the log of the base. So you can use either one. So that's called the change of base formula. And the rest of the notes were just about being able to practice using that if you need it. So if you wanted to evaluate log base 2 of 6, you could do log of 6 divided by log of 2. Go over here onto my calculator. I could do log of 6, which would be base 10. To make it base 2, just divide by log of 2. Okay? Now again, those of you that have the newest versions of the calculator, you can hit alpha and the window button and choose number 5, and you can actually set up log base 2 of 6 and not have to use change of base. But not everybody has this calculator, so we still teach the change of base formula. Okay? And you want to be able to do more complicated expressions, so we could do -3 times. I want to do log base 4 of 12, so I could do log or natural log of 12. Close it up. As soon as you close the log, divide by the log of the base you want it to be, and you'll get your value and round to however many decimal places you want. Okay? And then here's an example. We want to graph logs. I could do this as transformations like we talked about in the previous section. But now if I wanted to do this on my calculator, let's see if I can adjust it so we can see everything here. I hit y equals, and let's do the one that looks most like the expression. I'll use the common log of x minus 1. As soon as you close off that logarithm, divide by the log of the base you want it to be. So we make it base 4. And then if there's anything left, like the +2, I add that on. And then I'm going to hit graph. I think it should be in the standard window. Okay. An important point I want to make here as well, calculators do a horrible job of graphing vertical asymptotes because all calculators do is take hundreds of points across the screen and find the y values and plot those. When you have an asymptote, it goes off to infinity or negative infinity so fast that it runs out of points to draw. So there's actually a vertical asymptote at 1 because of the x minus 1 moves it forward 1. So there's this imaginary vertical line here at x equals 1 that the graph, it's going down. That graph does not stop like a square root. It goes down forever toward negative infinity. So when you actually draw this, you should draw a dotted line at 1 and then a little arrow on the end. But anyway, there's what it looks like.